Hello and welcome to this revision session for AQA A-Level Physics Paper 2 on the topic of thermal physics. So if we've been successful and we've learnt in today's revision session, we should be able to answer A-Level Physics examination style questions, assess our understanding on A-Level Physics and understand what topics we need to improve upon for A-Level Physics. So how should you prepare for this revision session? When you're completing this revision session, divide your piece of paper into two sections. Make the section on the left hand side larger than on the right hand side. In this section, please ensure you write down your working out answers to the questions in your revision session. When you're doing this, make sure you write in full sentences and show your full working out. Whilst in the right hand side, write down any bits of information which you find useful or any hints and tips on answering questions from this revision session. After the end of the revision session, write up these notes into a revision sheet for you to use independently. So how should you be revising for your A-Level Physics? So the first step is to learn the key facts. Use revision guides, class workbooks, student prep notes and the textbooks to learn the key ideas of the course. Now you may wish to make mind maps or to write out notes yourself. Then test yourself. Use things like Caboodle, Seneca, student knowledge checkers to quickly test your own knowledge, and you may wish to do this from your own cue cards. Then use exam preparation books, homework books, supervised study books, additional workbooks to answer examination questions and mark your own work, and you may wish to download your own exam past papers to do this. So learn the key facts, test yourself, and practice exam style questions. So what are the key facts to do with thermal physics? Well, in thermal energy transfer, we know that the internal energy is the total kinetic energy and potential energy of the particles in a system. We know that internal energy will increase when heat is transferred into the system or work is done on the system. So the change in internal energy is equal to the energy added as heat plus the work done on the system. Now, during a change of state, the potential energy changes, but the kinetic energy remains constant. This leads to no temperature change. Now this means the energy required to cause a temperature change is equal to Q equal mc delta theta, whilst the change of state, which is linked to the latent heat, is equal to Q equals ml. Now for ideal gases, we know the gas laws are Boyle's law, which is where P is proportional to 1 over V at constant temperature, and Charles's law, which is V is proportional to T at constant pressure. Now absolute zero is a theoretical temperature at which particle motion will fully cease. Now our ideal gas equations are PV equals nRT for moles and PV equals nKT for molecules. Now the work done by a gas is equal to the work done equals the pressure times by the change in volume. You must be aware of the molar mass and the molecular mass, and then how to use Avogadro's constant. Now in terms of molecular kinetic theory, Brownian motion provides experimental evidence for the existence of atoms, the irregular motion of smoke particles under a microscope caused by unseen gas molecules. You must be able to link P, V and T to microscopic behaviour, so it explains macroscopic gas laws using a molecular model of particles in constant random motion. Now, the gas laws are empirical based on observations, whilst the kinetic theory derives relationships from first principles using physical assumptions. Now, the internal energy of an ideal gas is the total kinetic energy of its molecules only. There is no potential energy. Now, again, scientific models evolve, so understanding of gases has changed over time due to experimental evidence and theoretical development. Now, the kinetic theory equation is PV equals 1/3 nm root mean square velocity squared. So the average molecular kinetic energy is a half mc RMS squared, which is equal to 3 over 2 kT, which is equal to 3 RT over 2 Na, or Avogadro's constant. Now, the assumptions of the kinetic model are that the particles are point masses, all collisions with walls in between molecules are elastic, there's no intermolecular forces except during collisions, the time of collision is negligible, motion is random and isotropic, it's the same in all directions, Newton's laws apply to the motion of the gas molecules, and there's a large number of molecules present. So let's have a look at some general check questions to do with thermal physics. So, what is meant by the term internal energy in a system? Internal energy is the total of the randomly distributed kinetic and potential energies of all the particles found within a body. How does heating affect the internal energy of a substance? Heating increases the internal energy of a substance, normally by increasing the kinetic energy of its particles. So what are the two ways in which the internal energy of a system can be increased? Internal energy can be increased by heating the system or by doing work onto the system, such as compression. During a change of state, what happens to the internal energy of the substance? Well, internal energy will increase because the potential energy of the particles changes, even though their kinetic energy stays the same. Why does temperature remain constant during a change of state despite energy being transferred? Well, because the energy is going into changing the potential energy store, which will be either breaking or forming bonds or intermolecular forces of attraction, not into increasing the kinetic energy. What is the equation used to calculate the energy needed to change the temperature of a substance? Well, Q equals mc delta theta, where Q is energy, m is mass, c is specific heat capacity, and delta theta is the temperature change. What does the specific heat capacity of a material tell you? It tells you the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree Celsius or 1 Kelvin. What equation is used to calculate the energy required for a change of state? Q equals mL, where L is the specific latent heat and m is the mass of the substance. What is meant by the term specific latent heat? It is the amount of energy required to change the state of 1 kilogram of a substance without a change in temperature. What is meant by continuous flow in thermal energy calculations? It often refers to scenarios where a fluid flows steadily through a system, often requiring ongoing heat transfer calculations based on the mass flow rate present. What is the relationship described by Boyle's law? Boyle's law states that for a fixed mass of a gas at constant temperature, the pressure will be inversely proportional to the volume. P is proportional to 1 over V. What does Charles's law state about the volume and temperature of a gas? Charles's law states that for a fixed mass of gas at constant pressure, volume will be directly proportional to absolute temperature. V is proportional to T. What is meant by the term absolute zero? Absolute zero is the theoretical temperature at which all particle motion ceases, and the internal energy is a minimum and it is only potential energy. It's equal to 0 Kelvin or minus 273.15 degrees Celsius. Write the ideal gas equation for a fixed number of moles. The ideal gas equation is PV equals nRT, where P is pressure, V is volume, N is moles, R is the molar gas constant, and T is the temperature in Kelvin. What is the alternate form of the ideal gas equation using number of molecules? Well, PV is equal to nKT, where N is the number of molecules, K is the Boltzmann constant. What is the equation for work done by a gas during expansion or compression? Work done is equal to P delta V, where P is the constant pressure and delta V is the change in volume. What is the significance of the Boltzmann constant K in the kinetic theory of gases? It relates the average kinetic energy of a gas particle to the absolute temperature, and it's used in the equation PV equals nKT. How is the molar mass of a substance related to its molecular mass? Molar mass in grams per mole or kilograms per mole is the mass of 1 mole of a substance and is numerically equal to the molecular mass in unified atomic mass units. What does the Avogadro constant represent? It represents the number of particles, atoms or molecules in 1 mole of a substance, and it's approximately equal to 6.022 times 10 to the 23. What does Brownian motion provide evidence for? Brownian motion provides evidence for the existence of atoms and molecules, as it shows particles being moved by invisible collisions with smaller particles. What does the kinetic theory model aim to explain? It explains the relationships between pressure, volume, and temperature of a gas using a theoretical model based on molecular motion. How do the gas laws and the kinetic theory differ in terms of origin? Gas laws are empirical. They're based on experimental observations, whilst the kinetic theory model is derived from theoretical assumptions. What assumptions are made in the derivation of the kinetic theory equation for an ideal gas? Particles are in random motion. The collisions are perfectly elastic. The volume of the particles is negligible, and no intermolecular forces act except during collisions. For an ideal gas, what is the internal energy equal to? The internal energy is equal to the total kinetic energy of the gas molecules. How is the average kinetic energy of a molecule related to its absolute temperature? It is directly proportional to temperature. As T increases, the average kinetic energy of the molecule increases linearly. What does the term CRMS refer to in the context of gases? It refers to the root mean square speed, a measure of the average speed of gas molecules accounting for their squared velocities. Why has the understanding of gas behaviour improved over time? Because scientific knowledge and technology has advanced, allowing for better models, better measurements and better observations of particle behaviour. For an ideal gas, why is internal energy considered to be only kinetic and not potential? Because in the ideal model, there are no intermolecular forces of attraction between the particles, so particles do not have a potential energy stored due to their position. Let's now have a look at a few questions concerning thermal physics. A cryogenic fuel tank on a spacecraft contains 2 kilograms of liquid oxygen at its boiling point of 90 Kelvin. During a test, a heater supplies energy at a constant rate of 120 watts to the tank for 600 seconds. The tank is well insulated and no oxygen escapes during the test. The specific latent heat of vaporization of oxygen is 2.13 times 10 to the 5 joules per kilogram. The specific heat capacity of gaseous oxygen is 920 joules per kilogram per Kelvin. Calculate the total energy supplied by the heater. Determine the mass of the oxygen that changes state from liquid to gas during the heating process. Explain why the temperature of the oxygen remains constant during the 600-second heating period. Then an engineer suggests that the temperature of the oxygen should have risen steadily from the start of the heating. Evaluate this suggestion. So, pause the video now, then unpause the video when you want to go through your answer. Right, we know the energy supplied is power times by time, so we work that through with 72,000 joules. Now the energy required to vaporize all 2 kilograms is E equals ml, and we said m to 2, so it's 426,000 joules. So what we can therefore say is that the mass vaporized is going to be m is equal to q over l. So therefore it's 72,000 over 2.13 times 10 to the 5, which is 0.338 kilograms. So it indicates to us that unfortunately we haven't been able to vaporize all of it. Now, not all of the liquid oxygen will vaporize. All energy therefore is being used to break intermolecular forces of attraction or bonds during this phase change, so the temperature remains constant at 90 Kelvin during this process. Finally, the engineer's suggestion ignores the latent heat of vaporization. The temperature cannot rise until all of the liquid has fully vaporized. A distillery uses a copper heat exchanger to condense ethanol vapor at 78 degrees Celsius into liquid ethanol. Cold water flows continuously through a coiled copper pipe to absorb the energy transferred as the ethanol condenses. The ethanol vapor enters the heat exchanger at 78 degrees Celsius and exits the liquid ethanol at 78 degrees Celsius. The mass flow rate of the ethanol vapor into the condenser is 0.050 kilograms per second. The specific latent heat of vaporization of ethanol is 8.5 times 10 to the 5 joules per kilogram. The water enters the coil pipe at 12 degrees Celsius and leaves at 48 degrees Celsius. The flow rate of the water is 0.120 kilograms per second, and the specific heat capacity is 4,200 joules per kilogram degree Celsius. Explain why the temperature of the ethanol does not change during condensation, even though the energy is being transferred out of the ethanol. Calculate the rate at which energy is transferred from the ethanol during condensation. Then calculate the rate of energy gained by the cooling water. Compare your results and suggest one possible reason why they might not match. If we decrease the flow rate of water, it will cool the ethanol more effectively because it will get hotter. Evaluate this claim. So, pause the video now, then unpause the video when you want to go through your answer. In our first one, energy is transferred out to overcome the intermolecular forces of attraction during phase change. Now, the potential energy of the particles decreases, but the kinetic energy and therefore the temperature must remain constant. We can work out the energy transferred from the ethanol by doing Q equals ml, and we get 42,500 watts, or joules per second when we work this through. The temperature change is therefore going to be 36 degrees Celsius, so the energy gained by the water is mc delta theta, or 0.12 times by 4,200 times by 36, which is 18,144 joules per second, or watts. So for comparison, there's a difference of 42%. Now, the possible reason is that not all of the energy is transferred to the water. There's losses to the surroundings, incomplete heat transfer, and the ethanol might not fully condense at the stated flow rate. Finally, lowering the flow rate causes a greater temperature rise in the water, but less mass per second of the water means that less total energy is absorbed per second, so therefore the energy transfer rate may actually decrease, so the claim is actually incorrect. A sealed high-altitude research balloon contains helium gas and is released from the ground where the temperature is 290 Kelvin and the pressure is 1 × 10 to the 5 pascals. The balloon has a volume of 2 meters cubed at launch. As it rises, the external pressure drops and the temperature decreases. At a certain altitude, the external pressure is 2.5 × 10 to the 4 pascals and the temperature is 230 Kelvin. The balloon is designed to expand freely and remain in thermal equilibrium with its surroundings. Assume helium behaves as an ideal gas. Calculate the volume of the balloon at this altitude. The balloon is fitted with a pressure sensor that records a sudden increase in internal pressure even though the external pressure continues to fall. Suggest a possible explanation for this observation. Then an engineer claims that the work done by the gas as it expands is equal to the product of the final pressure and the change in volume. Evaluate this claim in the context of the balloon's ascent. So, pause the video now, then unpause the video when you want to go through your answer. In our first answer, how can we work out the volume of the balloon? Well, we can say that V2 is equal to P1V1T2 over P2T1, so it's just using the gas laws. Pop in all the values and we get 6.34 meters cubed. Next one, a sudden pressure will increases that there's going to be a heating or compression. Now, a solar heating or the balloon reaching the elastic limit could cause an internal compression. Now, the ideal gas law assumes equilibrium conditions, and that may not apply during the rapid changes. Finally, W equals P delta V is only valid if the pressure of the gas remains constant. In this case, the pressure changes continuously during the ascent, which therefore means that it can't actually be used in this context. A student investigates how the pressure of a fixed volume of gas changes with temperature. They trap a small amount of dry air in a sealed rigid container and measure the pressure at various temperatures. The graph below shows the pressure P against the temperature theta in degrees Celsius. Explain how this experiment demonstrates the concept of absolute zero. In your answer, refer to the behavior of the particles in the gas. Use the data to determine an experimental value for absolute zero in degrees Celsius. State and explain one reason why the value obtained in A1.2 may not be exactly equal to the accepted value of minus 273 degrees Celsius. So, pause the video now, then unpause the video when you want to go through your answer. Right, in our first question, what's happening at absolute zero? Well, as temperature decreases, the pressure will decrease, indicating that particles will have less kinetic energy. At absolute zero, the particles have the minimum possible energy and exert no pressure whatsoever. So extrapolating the pressure-temperature graph to zero pressure estimates the temperature at which the molecular motion stops. So we would work out the gradient, so we would do 35 over 100, which is 0.35 kilopascals degrees Celsius. We can use the equation of the line where we get y equals mx plus c. So we can say that P equals 0.35 theta plus 100. So we set P to equal 0, because we know at absolute zero the pressure is equal to 0. Pop that in and we get theta to be coming out to be minus 285.7 degrees Celsius. Right, and that last one, air is not an ideal gas. Real gases deviate from ideal behaviour, especially at low temperatures. And in addition, we're extrapolating beyond the measured temperature range, which introduces an uncertainty into the calculation. Now, there could also be experimental errors, such as leaks, non-uniform heating, and instrumental calibration issues, which could also affect our result. A vacuum chamber is slowly filled with a monoatomic ideal gas. The gas is initially at a temperature of 300 Kelvin and reaches a pressure of 1.20 times 10 to the 5 pascals when the volume is 0.050 meters cubed. The total number of gas molecules in the chamber is 1 times 10 to the 23. Calculate the root mean square speed of the gas molecules in the chamber. The molecular mass of the gas is 0.020 kilograms per mole. The calculated root mean squared speed differs from the value predicted using the ideal gas equation. Suggest two reasons for this discrepancy and explain why this doesn't necessarily contradict the ideal gas model. Then a student claims that increasing the temperature of the gas will increase the pressure because the molecules hit the wall harder. Evaluate this claim. So pause the video now, then unpause the video when you want to go through your answer. In our first answer, we can work this out by using the equation m is equal to molar mass over the Avogadro's constant. So we pop that through and we get 3.32 times 10 to 26 kilograms. We know that C RMS is equal to square root 3 PV over nm. We pop in all the values and we get 516 meters per second. Now, the kinetic theory and ideal gas equations are based on different assumptions or simplifications. Now, real gas effects such as intermolecular forces, non-zero particle volume will affect the result. In addition, experimental or measurement uncertainty can also cause this. So there's two possible reasons. Now, finally, increasing the temperature increases the average kinetic energy. This leads to more frequent and more forceful collisions with the container walls. A sealed container of fixed volume contains nitrogen gas at a temperature of 300 Kelvin. The number of nitrogen molecules in the container is 6 times 10 to the 23, and the mass of one nitrogen molecule is 4.7 times 10 to the minus 26 kilograms. Calculate the total kinetic energy of the gas molecules in the container. Explain how the molecular kinetic theory model accounts for the pressure exerted by the gas on the walls of the container. Discuss two assumptions made in the molecular kinetic theory model of an ideal gas. For each assumption, explain how the behaviour of a real gas may differ from the ideal case. So pause the video now, then unpause the video when you want to go through your answer. In our first one, we can say E is equal to 3 over 2 kT. That's the kinetic energy of the gas molecules. So you pop it all through and you get 3.73 times 10 to the 3 joules. Now, molecules will move in random directions with a range of speeds. So the molecules collide elastically with the container walls. So each collision will change momentum as they change in direction, so it exerts a force on the wall. The pressure is then due to the net force from all the molecular collisions over the container surface area. Now, the ideal gas assumes no intermolecular forces. Real gases do have attractions, especially at a high pressure or low temperature. The ideal gas also assumes that molecules occupy a negligible volume. Real molecules do actually occupy a space. In the early 19th century, gas laws such as Boyle's law and Charles's law were discovered experimentally. These laws described how the pressure, volume and temperature of gases were related, but provided no explanations of why gases behave this way. Later, the development of the kinetic theory model and the observation of Brownian motion helped scientists to understand the microscopic behaviour of gases. Describe how the observation of Brownian motion provided evidence for the existence of atoms or molecules. Explain why the gas laws are described as empirical and how the kinetic theory model provides a theoretical explanation of gas behaviour. Then discuss how our understanding of the behaviour of gases has changed over time, referring to both experimental evidence and theoretical developments. So pause the video now, then unpause the video when you want to go through your answer. Right, in our first question, we can say that Brownian motion refers to the random movement of visible smoke or pollen particles suspended into air or fluid. The motion is caused by collisions with much smaller invisible gas or liquid particles, atoms or molecules, so this provides indirect evidence for the existence of motion of individual atoms or molecules. Now, the empirical laws are based on observed experimental relationships. For example, P is proportional to 1 over V at a constant temperature. These laws are describing what happens, but not why. The kinetic theory model is based on theoretical assumptions about particle motion and collisions, so it does explain gas behavior in terms of microscopic motion and the energy of gas particles. Now, early models treated gases as continuous substances with no understanding of their microscopic structure, that they were made from particles. Experimental observations, like Brownian motion, supported the idea that they were made from particles. The kinetic theory introduced a model that explained pressure and temperature in terms of molecular motion and energy. Over time, quantitative predictions align with the theory with the experiment, leading to widespread acceptance. 50 years ago, Henri Pétry developed a device for the kitchen that produces instant boiling water. A modern version is shown. The system consists of a small tank connected to the water supply. Water in the tank is heated under pressure to a temperature of 110 degrees Celsius. When the water flows out of the tap, the temperature falls to 100 degrees Celsius. Water enters the tank at a temperature of 12 degrees Celsius. An electric heater increases the temperature of the water to 110 degrees Celsius. The water does not boil because it is under pressure. Calculate the time taken to heat a full tank of water to 110 degrees. So, pause the video now, and then unpause the video when you want to go through your answer. Right, in our first one, what we can say is E is equal to P times by T. So therefore T is equal to E over P, and we know E is equal to mc delta theta, and P is equal to Vi. We know mass is equal to density times by volume, because you're given the density and the volume in the question. So you can pop in all the values and work it through. Now remember, delta theta is the change in temperature. So you pop in all the values and we get 423 seconds. The next question says that when the water flows out of the tap, the temperature falls to 100 degrees Celsius. The average rate of energy transfer from the tank to the surroundings is 9.5 watts. A full kettle contains 1.4 times 10 to the minus 3 meters cubed of water. It takes 180 seconds to bring a full kettle of water to 100 degrees Celsius. The kettle is used to bring enough water for 28 cups of tea to 100 degrees Celsius. A reviewer compared the energy transferred from the tank to the surroundings in 24 hours with the energy transferred by the kettle to make the tea. A reviewer claimed that the energy transferred from the tank will be greater than the energy transferred by the kettle. Assess the validity of this claim. So, pause the video now, then unpause the video when you want to go through your answer. Right, in answering this question, we can work out the energy transferred from the tank, which we know is P times by T. So from the information given, and we're told that's in 24 hours, so we convert our hours into seconds, we get our answer to be 8.21 times 10 to the 5 joules. Now we can also then work out the volume needed for 28 cups of tea. So it's 28 times by 3.5 times 10 to the minus 4. So it's 9.8 times 10 to the minus 3 meters cubed. Now the number of kettles required will be that value divided by the capacity of one kettle, which is 7. So the time for the kettle to be switched on is 7 times by 180 seconds, because we're having 7 of them and they've got to be on for 180 seconds each at a time. So that's 1260 seconds. So the energy transfer to the kettle is power times by time, which is 3.28 times 10 to the 6. So what we can say is that 3.3 times 10 to the 6 joules is greater than the energy provided, which is 8.2 times 10 to the 5 joules. So our claim just is not valid. The next question says ice cubes can be made in an ice tray. One type of ice cube tray is shown. Each compartment in the ice cube tray has dimensions of 2.5 centimeters by 2.5 centimeters by 3.5 centimeters as shown. Show that the mass of the water needed to fill one compartment is about 0.020 kilograms. All 6 compartments in the ice cube tray are filled with water to a depth of 3.5 centimeters. The ice cube tray is placed in a freezer. The initial temperature of the water is 22.5 degrees Celsius. It takes 12 minutes for all the water to become ice at 0 degrees Celsius. The manufacturer of the freezer states that the freezer can transfer energy at a rate of 110 watts. Evaluate whether the energy is transferred from the water in the tray at a rate of 110 watts. So pause the video now, and then unpause the video when you want to go through your answer. In our first question, we would say density is mass over volume. So therefore, we can say volume, we can work it through to be 2.5 times 10 to the minus 2 times squared times by 3.5 times 10 to the minus 2, which is 2.2 times 10 to the minus 5, or meters cubed. So therefore, we can then pop that in and say mass is going to equal to density times by volume. We've got our density, we've got our volume, so our mass is 0.0219 kilograms. We know the energy needed to change temperature is E is equal to mc delta theta. We pop in all the values. Remember, our delta theta is the change in temperature, so it's 22.5 Kelvin. So therefore, it's 1.224 times 10 to the 4 joules. The energy required to change state as it freezes is ml. So we pop that in and we work the answer through to be 4.41 times 10 to the 4 joules. Now remember, in both cases, there are 6 ice cubes, so you've got to multiply both values by 6. Now the power is equal to the energy divided by the time. Now the total energy is both the energy stored from the latent heat, which is the potential, plus the energy stored from the kinetic, which is the specific heat capacity one. Add the two together, divided by the time, which is 12 times by 60. So then we can work it all through, because it's 12 minutes, we want it in seconds. So we get our answer to be 78.5 watts. So that brings an end to our revision session today. If we've been successful and we've learned in today's revision session, we should be able to answer A-level physics examination style questions, assess our understanding on A-level physics, and understand what topics we need to improve upon for A-level physics. So thank you so much for watching this revision session on AQA A-level physics on the thermal physics topic, which is part of paper 2. Thank you so much for watching and have a lovely day.